Well, welcome. And so let's continue talking about the historical progression. I think it's hard for us to understand in this modern era the change in the world and in science that was occurring from 1900 to 1940. A real change in physics, for example, classical physics versus the new quantum physics. Classical physics works fine in describing the motion of and behavior of large objects. But when you go to small objects, atoms, for example, we realized that classical physics didn't work. And that led to a lot of advances, a lot of discoveries, a lot of new ideas. And so we were talking about Einstein. Einstein was Jewish, a very important scientist in Germany, and he published general relativity and published this in 1915, general relativity, that space is curved, that when you're near a massive star, even something without mass, like a pulse of light, would be deflected by the mass of that star. Makes no sense if you just consider that pulse of light. That's a photon, that's a wave that has no mass. How would that be affected by the force of gravity? The answer is the intense gravitational field of that big massive object, a star, a black hole, a neutron star, whatever, curves the space around it. And so then things do not move in what I consider to be a straight line. Things move in a curved line around, following that curved space. That was his prediction. A lot of people thought that was crazy. That was then verified by that expedition to the Pacific when Lord Eddington went to the Pacific so that he could see an eclipse of the sun in 1919 after World War I had ended, and realized that two stars in the sky displaced by that amount. Yeah, somebody's out there probably should mute your computer. I unmuted everyone's computer on Zoom by mistake. And so I hear somebody rustling around. So you need to mute your computer. So what they found, Lord Eddington found, was that those two stars were in a different place. Instead of being, this is where they actually are, but the light there curved around the sun. And you can see the two stars because the sun is eclipsed. And so those two stars extrapolated back with the eye, a straight line, appear to be that far apart instead of this far apart. That was a sensational discovery. It proved that space was curved around a massive object. It proved that Einstein was correct. It proved that general relativity was correct. And Einstein became a rock star, so to speak, overnight in the popular press. And so general relativity was verified. And then he also predicted gravitational waves. We talked about that a little bit last time. I never thought that this would be found, verified, and discovered in my lifetime, but it has been. His idea is not only the space curve, but if you have two massive objects like neutron stars colliding, that collision produces a change, a ripple in curved space-time. And so that ripple and the curve for space proceeds out for billions of years. And we've detected that now on Earth. It's a remarkable experiment by interferometer, one based in Louisiana, one based in the state of Washington, where they saw such a very minute ripple, a change in distance between one of these legs of this pathway of the laser by a fraction of the diameter of a proton, because that space there, under it, around it, the Earth, everything in that space for that moment changed its dimension because of that gravitational wave that was going through Earth at that moment. So that's been verified. And so that's a big step forward. Then Einstein in 1905, one of his 4 great discoveries was special relativity. General relativity refers to the curvature of space in the vicinity of a massive object. Special relativity refers to the fact that the speed of light is the same for all frames of reference, whether you're stationary or moving. And that's a real constant nature, speed of light, 186,000 miles per second. It takes a pulse of light 8 minutes to get from the surface of the sun to Earth. So the speed of light is not infinite. It's large, 186,000 miles per second. And that's why it takes 8 minutes from the sun. But that's an absolute constant in nature. So if 2 frames of reference were measuring something, they would see different things because the speed of light cannot be exceeded. And so this leads to the fact that clocks tick differently if you're moving toward the speed of light. And length is measured differently if you're a fastly moving object. And you know, if you're just bouncing a pulse of light off of a mirror and back from here, you've got a clock that takes a certain amount of time to go that distance at the speed of light. But if this clock is moving, then you've got a longer pathway for that pulse of light to travel. The speed of light is the same, but you've got a longer pathway, and therefore the clock tells you something different. So the clock might say that it's 1 second to the mirror and back for that reflected pulse of light. That's 2 seconds. But if you're moving at 90% of the speed of light, when you measure your clock in that frame of reference, you get 2.29 seconds instead of 2 seconds. Well, that's special relativity. And so that leads to the fact that aging is different. If you are observing this in the same frame of reference, you get 1 second, but in a different frame of reference, you're aged by 2.29 seconds. And so that leads to this conundrum that somebody who, let's see, did I have a slide on that? That if you set up a spaceship and you go a distance to the next star, which is 4.5 light years from our star, that if you're traveling at 86% speed of light, if that were possible, that we would measure that the time taken would be 2 times to go, for that pulse light to go to out and back would be 2 times the distance divided by the velocity of light, and that would be 10.3 years. But on the ships, the clocks on the ship, you have this relativistic effect. And the result is that the time that your clock would measure 5.14 years on the spaceship as opposed to 10 years if you're moving at 86% of the speed of light. And therefore, you age more slowly. The identical twin, you know, the twin goes on the ship, spaceship, moving at 86% of the speed of light, comes back, and he or she is aged half as much as his twin brother on Earth. Well, that's special relativity. Yeah, Phil.
So but the person on Earth would think they're aging more slowly, but they would think the person on Earth is aging more slowly, wouldn't they? Because the relative velocity is the same for them. And Dr. Keith once explained in a lecture that what that called the time
Time dilation.
In dilation, but there's a conundrum. The reason that they really do age less is because of acceleration and deceleration.
Correct.
Is that correct?
That's right. That's right. It's acceleration and deceleration. That once you're moving at 96%, 86% speed of light, then that's okay. But the change occurs when you accelerate to get up to that high velocity and then decelerate. Right. So it's very hard to understand, but special relativity.
So if we could go fast enough, we wouldn't age as quick.
Correct. Correct. In that frame of reference, right. Right.
We'd have other problems, yes.
So Einstein became the most famous scientist in the world. And this whole business of quantum mechanics, relativity, radically new concepts in the world of physics. And it was, for example, Einstein, a Jewish physicist, who was pushing this. And so there was this built up, I'll tell you more about it, this built up discrimination against the Jews in Germany and in other countries, but this extended over even to physics, that this was called the Jewish physics, relativity, quantum physics. And the traditionalists, the old time, even German physics professors, derided this new Jewish physics. So politics and science got mixed up. Einstein, of course, was German, but then his family went to Switzerland. He renounced his German citizenship in 1901. Then he got his degree, published those seminal papers in 1905, when he was working in Bern in Switzerland in the patent office. He was then brought back to Germany, became a German citizen again in 1914 when he became a chair professor. You know, he was now famous, got the Nobel Prize due to one of those 4 papers in 1905. He then, he's also a passionate Zionist, searching for a place for the Jews to call their homeland, since they've been booted around the world so much over hundreds and thousands of years. And so he came actually to raise money for finding a Jewish homeland. Things are bad in Germany, though. The foreign minister in Germany, who was Jewish, and a chemist, was assassinated in June of 1922 because he was Jewish. And Einstein figured he'd be next. By 1922, he was a world famous, most famous scientist in the world. Hitler took over the Workers' Party, I think it was called, and published some radical concepts or doctrines for the Workers' Party. Was put in jail and writes while he was in jail, not a hard jail, but a self-comfortable jail, Mein Kampf, I struggled while in jail. A big, long, lengthy publication that's a diatribe and illogical and racist in most ways, mostly pointed on the Jews. We'll come back to some of this, but then he, 10 years later, his party, the Nazi Party, had won an election. He was appointed Chancellor of Germany, and that began very quickly a change in laws in Germany, such that people, Jews who were public servants, working as lawyers or physicians or professors, were eliminated from their jobs because of this law on the restoration of professional civil service, first of many anti-Semitic laws that the Nazi Party in power produced in Germany. And so a quarter of all physicists lost their jobs, for example, in Germany. 406 dismissals of professors primarily in physics and biology. So times were changing rapidly in Germany. And this is expanded on it, and maybe I've said most of this already. So the older professors, German professors, derided relativity as not very really real. It's just some of this Jewish physics that is being propagated. And this was all built upon centuries of mistreatment of the Jews in Europe and elsewhere. You know, in the 1100s and 1200s, the Catholic Church viewed the Jewish religion as evil and counter to the Catholic religion. So the Catholic Church led mistreatment of the Jews in the 1100s and the 1200s. So this was not a new thing in Germany. There was the Black Plague in Europe in the 1300s, where a quarter of the population of Europe died because of the Black Plague. Well, by many people, many countries, they blamed it on the Jews. Somehow this was, Black Plague was all of the Jews in those societies. And tens of thousands of Jews were then killed in retaliation for the Black Plague. Jews were kicked out of England in 1290. They were kicked out of France in 1390, Spain in 1490, and Portugal, and so on. And so this mistreatment of the Jewish people in these various countries had built over centuries. Not just something Hitler came up with in 1933. So that's the issue. You know, where would the Jews be able to live? Because they were cleared out of these various European countries. Eventually, they ended up in Poland. And that became a place where the Jewish people lived for a long time in relative peace. The population grew. Russia, of course, has taken over Poland X times in the history of Poland. Poles live in constant fear that the Russians will be coming tomorrow to take over their country once again. And so this had happened then, in this period. That time, Russia took over Poland, around 1 million Jews who were living there in Russia, in Poland, now Russia. And Catherine the Great called them the enemies of Christ. So she viewed them as a threat to her country. In 1825, Nicholas I of Russia decreed that Jewish boys would be conscripted into the army at age 12. They would be then educated for 6 years, and then they would have to serve for 25 years in the army. Well, this was slavery, essentially. 50,000 such boys over the next 30 years were conscripted into the Russian army. So another mistreatment of the Jews. Finally, that was relaxed in 1856. But that specter of abuse persisted. So when Edward Teller, one of those Hungarian Jewish boys that became a great scientist in the US, when he got out of line, his grandmother would say, you know, if you don't behave, the Russians are going to come and get you and conscript you into the army, the Russian army. Mid-1800s, things got better a little bit for the Jews in Europe. It was the age of Enlightenment. There was emancipation of the Jews in a number of countries in Europe. However, then things took a turn for the first when Tsar Alexander II in Russia was assassinated in 1881, and that was blamed on the Jews. Maybe one of the assassins may have had somewhat of a Jewish background. It was hardly a Jewish plot. And so there were retaliations that accelerated against the Jews after that assassination. Immigration started in 1900, between 1900, or by 1900, 1 million Jews from Europe came to the US. Between 1920 and 1.5 million. So Jewish immigration to the US occurred primarily at that time, and because of the assassination of Alexander II, upped the pressure on the Jews after a relatively calm period. Along about that time, probably somebody reporting to the Tsar of Russia wrote a bogus book called The Protocols of the Elders of Zion. And this is purported to be the blueprint for Jewish domination of the world. Now, this is bogus entirely, but gee whiz, it's fake news. And so this book was written probably by a Russian, and then was translated in many languages in Europe. And people believe this. This was the blueprint for the Jews taking over the world. And that then was, translated, brought to Germany. And Hitler seized upon that bogus book as why a rather small part of the population, the number of Jews in Germany was not large, it was less than 1% of the population. So why did it become such a problem in Germany? It wasn't Poland or Russia, where you had a lot greater percentage of Jews there. But Hitler seized upon this bogus book as the reason that the Nazi Party had to get rid of the Jews, because they were going to take over the world. This was their blueprint. One purpose of this bogus book was to discredit constitutional governments that had sprung up in Europe in the Age of Enlightenment, which all sounds very familiar with the real world. Russia moved to a more democratic. Putin came back in. We're back almost to the days of the Tsar. Well, that's what happened here also, where this book was written to discredit liberalism that sprung up in the middle 1800s in Europe, the formation of constitutional governments where people had a voice in who would govern them, and wanting to go back to the old days of kings and czars. It's amazing now. So, and actually, Hitler apparently admired this blueprint and more or less adopted it to the Nazi Party. The blueprint, this bogus blueprint that was supposedly there for the Jews to take over the world. And somehow then even the new physics, I still find this hard to believe, I do not understand it, but this is some of the background, even the new physics was lumped into this Protocols of the Elders of Zion. This was one way the Jews would take over the world, by inventing a new physics. So that was discredited. That was part of the conspiracy plot by the Jews, apparently. Hitler became Chancellor of Germany in January 1933. There was the fire, the Reichstag. Some people say set by the Nazis. That enabled, by that fire, that he was able to go to the parliament, so to speak, and have them grant him full powers because of this natural emergency. And then he was able to really go forward rapidly in suspension of civil liberties and passage of many laws of anti-Semitism in Germany. He called for a national boycott of Jewish businesses already on April 1st. In a couple of parts of Germany, right away, Jewish judges and lawyers were dismissed. This law was passed on April 7th. After that, 1,600 scholars were affected. Over 400 professors lost their jobs instantly. And so, these great scientists like Einstein no longer comfortable. Einstein had already left Germany, but many others had to leave Germany after this. So these Hungarian Jews that all went to Germany to get their science training, became great scientists, they scattered on Kármán, one of those 7 people from Mars, so to speak, by the tongue-in-cheek book. The great Hungarian Jewish scientists that all came from near Budapest, middle-class families. On Kármán was hired at Caltech in 1930. He became the head of the aeronautical effort at Caltech. Einstein accepted a position at Princeton, and the new Institute for Advanced Studies was built around him in 1932. He was the most famous scientist in the world then. Von Neumann and Wigner had already been to come to Princeton in 1930. Szilard went to England. Hans Bethe, another Jewish German scientist, not Hungarian, came to Cornell. Teller worked under Heisenberg and then finished his degree and then went to London and Copenhagen. Otto Frisch will come back to, he was the nephew of Lisa Meitner, who was Austrian, therefore protected somewhat from the craziness of Nazi Germany until Germany took Austria. And over that time, maybe 100 physicists in the early 30s came to the US. And, you know, somebody that a famous Jewish politician said that the French will pray for the displaced Jews, British will organize their rescue, and the Americans will pay for it. So that's pretty much what happened. The US, you know, the recession had ended, and so there was money to bring a lot of these excellent scientists to the US, which then had great impact on the Manhattan Project. Huge impact to enable us to succeed in the Manhattan Project. So Becquerel started, Marie Curie, Pierre Curie, Rutherford, they knew that there was natural radioactivity. You know, and that's how Marie Curie found the elements polonium and radium. They're naturally radioactive. She isolated them chemically. She paid for it with her life when she died at age 67 because of all the radiation she had handled. But she figured out that it was two new elements, polonium and radium, that were naturally radioactive. And we understand that now. Uranium is naturally radioactive. And potassium-40, you know, there's radioactivity in concrete blocks called potassium-40, it's long-lived. So we're surrounded by low levels of radiation. That's how we have evolved on Earth, you know. That maybe was an aid to our evolutionary development as humans over millions of years. So a lot of elements in the ground have natural radioactivity. The advance here by Marie Curie's daughter, Irene married Frederick Joliot, and they worked at the Radium Institute. Radium Institute was started by Marie Curie after she got her 2 Nobel Prizes in Paris, near the Sorbonne. And Irene, after Marie got older and sicker, Irene ran the Radium Institute, and their big advance, their Nobel Prize in 1935, Irene and Frederick Joliot-Curie, was the first fabrication of artificial radioactivity. So that was the next frontier. How do you do something to make a radioactive nucleus? Well, the way they did it, they took a piece of aluminum target, they hit it with alpha particles from polonium. See, these decay, these have alpha decay, long half-lives. helium. Helium-4 nucleus. And so those give off radiations that you can then focus and hit upon a target. And then they realize that they made something new. By this time, the neutron had been discovered, so they made an isotope of phosphorus. So this, they got the Nobel Prize for the first artificially produced radioactivity. Well, then came the story of Enrico Fermi. Enrico Fermi was an Italian. Short, smart, and got appointed to the faculty, to professorship at the University of Rome at a very young age. Probably around 30 years old, as I recall. And Rome, University of Rome did not have a real reputation in physics at that time. So that's why he was able to do this at a very young age. And he was really good. He was given a large budget. He was given a terribly high budget, $2,000 to start a physics lab in Rome. Now, 1932, the neutron was discovered. Fermi, didn't quite know when he started building this physics effort in Rome in 1926. He didn't know what would be the focus of his research, of his discoveries. But then Chadwick discovered the neutron in 1932, and then he realized, gee whiz, the neutron could be a better way than an alpha particle to induce artificial radioactivity. See, the problem with using an alpha particle is it's got a charge. It's got 2 protons, 2 neutrons. 2 protons, 2 neutrons. You shoot it, let it impinge upon a target, a balloon or whatever. You've got the electrostatic repulsion between the protons in the helium nucleus and the protons in the target nucleus. So they repel each other. Fermi realized that the neutron had no charge. So if you're trying to make artificial radioactivity, it's a better bet to use because it's not repelled by the target nucleus. That was his big innovation. So he figured out a way to do this. Take an alpha source, one of these, polonium or radium. You train that emitted alpha particles on a 4 beryllium, and it turns out this is how Chadwick discovered the neutron. The first what comes off there when alpha particles hit beryllium, they thought they were gamma rays. Curie's, Jolyon Curie's missed the Nobel Prize because they thought these were gamma rays. Was Chadwick worked in Rutherford's lab in England, realized there were neutrons, and thus the discovery of the neutron in 1932. Well, now Fermi understood that, and so you use these flux of neutrons, naturally a radioactive alpha emitter, put in a beryllium foil, use that then, put different targets here, and let neutrons from that rig hit different targets. And that worked. So they took samples of everything they get their hands on, different elements, different minerals, and put it in beams, this beam of neutrons. Then they would take it out after some irradiation. They would take the target out, run down the hall to a Geiger counter, and count the activity. You measure its half-life then too, of how quickly that activity died away. And so that's what they were measuring, making new radioactivities, new half-lives, when you put different foils in this flux of neutrons. And he did a whole series of experiments. He was able to get a strong polonium source. He did the geometry right. He figured he was getting 100,000 neutrons per second coming out from the beryllium foil and hitting his targets. And they bombarded 60 different elements in nature that way with neutrons. And they found many new activities. They found new activities in 40 of those cases. They published a number of papers on artificially produced radioactivities with different half-lives by neutrons hitting different elements in nature. By accident, they found the important role of moderating neutrons. You see, now we understand this. Now that's how power reactors work. Now we know when uranium fissions, it gives off 2 or 3 neutrons per fission, that you have to slow them down, moderate their energies to increase the likelihood that they will cause other radionuclei nearby to fission. And so that's how our nuclear reactors work. Water, H2O, is the moderator and the coolant. Well, Fermi realized the importance of moderation by mistake. They were doing these experiments. Sometimes they got the same results, sometimes they got more activity, sometimes less. What was the difference? Well, it turned out the difference was the fact that sometimes they set their equipment on a wood table. Sometimes they set it on a brass table. Luckily, Finley had a lot of brass. And so sturdy brass top tables were common. And that was the reason for the difference. In other words, wood has touches moisture in there, water vapor. There's a lot of hydrogen atoms in the wood, more than a slate table. And finally, Fermi figured this out, that it was hydrogen in the wood that was slowing the neutrons down and increasing the likelihood that they would be captured and make new artificial radioactivities. And people joke that if he'd been doing this experiment elsewhere, then they had a lot of rest. Everybody would been doing it on a wood table. It would have been much longer to figure this out. And that's the very core, the key for building now a reactor, is what moderator to use to slow down the neutron. So that was an accidental discovery. They marched up the periodic table, putting different foils in the flux of neutrons. They got a stronger source, and we're up to maybe 1 million neutrons per second hitting different foils. When they got to uranium, heaviest element in nature, L92, they found 3 new activities, half-lives of 1/1300 minutes. They did some rudimentary chemistry on that irradiated foil. What was the element that was producing these new activities? They did chemistry. It was not element 91 or 90 or 89, things below uranium. So they thought that he's now discovered the first element beyond uranium, a new element. He happened to be giving a talk before the King of Italy, and the King of Italy got very excited. Somebody in his Roman laboratory had discovered a new element. Big deal. And so that was published in February 1935. The discovery of something beyond uranium. Fermi assumed that neutrons were captured on uranium-238, making uranium-239, but then beta decay to L93, and then probably to 94. So this was a big deal, this publication, February 35, that for the first time in this experiment, apparently, people had produced the first element beyond uranium. It does not exist in nature. Now, the question was, what was the chemistry of this new element? This is the periodic chart, periodic table as it appeared in 1935. A lot of holes there. You talk about this hole and this hole that weren't discovered yet. But you see, element 93 or 94, it had the chemistry of manganese, or the chemistry of iron. uranium has the chemistry of chromium. But these all have similar chemical properties, different classes. And so, but it didn't make a lot of sense that it seemed that after more experiments continued, that this new thing produced had the chemistry of barium or lanthanum. And that was just impossible to understand. How could neutrons on this, probably maybe this or this, or maybe this or this somehow, but to have something that had the chemistry of barium or lanthanum was totally beyond understanding. It produced a whole lot of interest in the world. But this discovery got Fermi the Nobel Prize in 1938. And that's right already. He was only 37 years in 1938, so he was only 26 when he got that professorship in Rome. Geez, that's when I started on the faculty. I was 26, but I didn't win Nobel Prize. So he got a Nobel Prize. That was good. He got a Nobel Prize because by 1938, Mussolini had taken power in Italy. He had a pact with Hitler, Italy and Germany. In Italy, by this time, if you were Jewish, you couldn't leave the country. You know, Hitler was driving Jews out of the country to get rid of these evil people. Mussolini, the law was if you were Jewish, you couldn't leave the country. And so Laura Fermi had a mother who was Jewish. And so by definition, she was Jewish, but somehow a mistake was made and her passport does not stamp Jewish. That's been a clerical error. And because of that, they were able to leave as a family to go to Stockholm in 1938 or 9 to accept the Nobel Prize. And then they didn't go back to fascist Italy. Then they came to the US. Fermi became one of the centerpieces of our Manhattan Project a few years later. The puzzle then by this time, by 1938, was what Fermi made when he hit uranium with neutrons seemed to have the chemistry of barium. And that made no sense. If you made this element 93, it should have the chemistry of manganese, 24 chemistry of iron, have the chemistry of barium. Made no sense. Szilard was one of these Hungarian Jews who came to Germany to get his PhD and then left Nazi Germany to go to England. He had trouble finding a scientific position, but he was a dreamer. He was the guy that knew H.G. Wells personally. He was a guy who talked to Wells about his novel in the late 1800s, predicted things in the future, including a great war and Germany versus the world and some weapon that would end the war in 1956. So he was a dreamer, a bit of a mystic in some ways, but he also was a physicist. And in 1934, he requested a patent on the idea that you might be able to chain reaction to release the energy of the atom. That if you could find an element that would absorb one neutron and emit two neutrons in the process in one of these nuclear reactions, like with Joliot-Curie or Fermi was working on, then you would multiply neutrons, absorb one and emit two. And then you would have a chain reaction, he theorized, that would then allow you to release quickly the high energy of the nucleus. So he filed for a patent in 1934. He then got some support in England and did some experiments. Thought maybe beryllium. The beryllium was that foil that people use to make neutrons without particles hitting it. He thought maybe beryllium would be that element that would allow multiplication of neutrons. That didn't work. And so he amended his patent application in 1935 to say that by his further thinking, the two best candidates for an element to possibly multiply neutrons and make a chain reaction would be uranium or beryllium. So he was ahead of the game. This was 1935. And we really didn't start down this road of trying to do something about the chain reaction in a bomb until more than 5 years later. Oops, wrong one, sorry. Got these two computers. Well, in chapter 9 of this book, they start talking about Lisa Meitner. She was Austrian, a single lady, never married. Science, physics was her passion. She worked in Germany, and she was head of the physics department at the Kaiser Wilhelm Institute in Berlin. Kaiser Wilhelm had in 20 years before set up a research institute in Berlin, and this was exceptional for the time. This woman was head of the physics department. Otto Hahn, bad picture here, was head of the Institute of Nuclear Physics within the physics department. And they worked together, Meitner and Hahn, German physicist, Austrian physicist. She was Jewish. She didn't make much of that, the Jewish tag on her due to a parent and or a grandparent, but she didn't grow up. She felt Jewish, but still that was on her passport, in her background. But she was safe from all the crazy new laws in Germany because she was Austrian. And so they worked together well, Hahn and Meitner in Berlin. They heard about the experiments of Fermi. Everybody heard about those experiments. A lot of people were working on trying to understand what happens when neutrons hit uranium. They brought aboard Fritz Strassmann, a young chemist in Berlin, to join their team, a nuclear radiochemist, nuclear chemist. Joel Curies were working on the same conundrum at the Radium Institute. And the point was that Fermi result just did not make sense of how something, element 93, 94, could have the chemistry of barium. Well, everything changed for Meitner when Hitler took Austria in 1938. So now she was a German Jew. So she had to go. She was no longer safe in Germany. At first she thought she could ride it out. A lot of scientists, a lot of intelligent people in Germany thought, well, we'll ride out this Hitler thing. He'll be gone soon. Life will return to normal in Germany. But her colleagues from Holland and other places came to Berlin and said, you've got to go now. She came to Copenhagen Niels Bohr arranged a position for her in Stockholm. So she went to Stockholm to work at Manny Siegbahns Institute. He had won a Nobel Prize for X-ray spectroscopy. And so she left in early summer of 1938 in the midst of these experiments that her group was working on to understand the Fermi result on uranium. So the experiments continued in Berlin, but she was now in Stockholm. By the way, element 109 is named in her honor, Meitnerium, MT. So she's also a great nuclear physicist. And of course, about the same time, Hitler was being very aggressive. He annexed Austria. And he was intent next on making an empire to include what he says were German territories that he lost in World War I, Czechoslovakia. And so then in 1939, he took those parts, the German parts of Czechoslovakia, to be part of his German empire, Austria, and now the German part of Czechoslovakia. Of course, the world, European governments objected, and a compromise was made where England and France agreed that he could have those parts of Germany, those parts of Switzerland, Czechoslovakia, that if there's at least half of the people that spoke German, that there could be a process to bring them into Germany. France already had a treaty with Czechoslovakia for self-protection, but they chose not to honor it. And England and France wanted self-determination, that those parts of Czechoslovakia could choose, could vote on whether they wanted to become part of Germany. And Hitler promised, of course, to Neville Chamberlain in September that, yeah, that he promised that he would allow those German parts of Czechoslovakia to choose what they wanted to do. And of course, Hitler didn't carry through with those terms at all. He just took that part of Czechoslovakia. They met, Mussolini, Hitler, Mussolini, there's Hitler, Chamberlain, must be Daladier, France, and Hitler said, okay, this is the last piece that I want. They disagreed that there was no self-determination in that German part of Czechoslovakia. Hitler said, okay, but that's all I'm going to take. Of course, all four of these countries agreed there'd be no war. That evening, after that meeting of these four leaders of these four European countries, Hitler and Mussolini met to plot the eventual invasion of Britain. So Hitler, of course, was trying to take over Europe, as he was promising that he would take no more than Austria and Czechoslovakia. So it's a very tense time. Of course, we all know about Chamberlain, who was criticized as being an appeaser. Maybe Ray, why don't you come and tell a story? Do you have a story to tell? I want to tell you about these experiments then, but I don't want to miss Ray's stories. So
This will be a short one.
Okay.
You're still out of time.
Okay, Ray, go ahead, tell your story.
Yeah, just to get you thinking again. It's too much trouble to find
No,
that.
it is not.
To find that silver slide we'll talk about it. During the Manhattan Project, these Calutrons that were set in 9 large buildings, and there were 1,152 of them. Now, this is a huge undertaking. And you've got General Groves being convinced by Ernest Lawrence that his Calutrons would work. They would do this separation that they were talking about and would produce that uranium-235. Now, the problem is, let's see.
What are you looking for?
Let's keep going.
Forward?
I think so. I'll come back to that one. Oh.
It's the last one.
Oh, well, then it's up to front. I'm so sorry.
The picture of
Must
what?
have been an earlier one. It could be a big picture of a coal.
Oh.
Oh, there, back up. That one's the one I'm talking about. Now, if you notice these large coals, and they're alpha Calutron coals. And you remember we had a picture that showed these alpha Calutrons. They were about 20 feet tall. Okay, the betas are about 10 feet tall. That's the two phases. You go through the alpha first and into the beta. And there were 5 large buildings that had alpha Calutrons.
Okay,
And
but
then
first,
four
Ray, let me
that-
ask, what were the Calutrons for? Who remembers that? What was their purpose? At Y12, what was the purpose of Y12?
Remember, you needed uranium-235 for fission. And you had natural uranium, has uranium-238, but it only has 0.7%, 235. And 1,000 pounds of uranium ore, you only got 7 pounds of uranium-235. Now, the 235 is what you need. So you've got to separate that. Remember, the Calutron is a very simple physics process with no moving parts. The uranium material goes in at the bottom. Because of these large magnets, that material gets bent one ion at a time. And as it gets bent, there you go. There you go. As it gets bent, the 238 makes a slightly larger arc than the 235. So you can separate those two. And the 235 is actually what you want. Now, to get that to work, they needed 11, and because it's so slow, it's a very slow process, they needed to build many of them to get it to work. It's all batch processes. Those 1152 work between 2 magnets. You put that material in, and the magnets cause it to beam. Now, think about all the magnets, largest magnets in the world. And think about all they had to have to build those magnets. And what were they going to wind those coils? These were electromagnets. What are they going to wind the coils with? Well, normally you would think of copper. That's an electrical conductor that works with. There was a shortage of copper during the Manhattan Project. They were using that copper for other purposes in the war, making weapons, other bullets, other things out of copper, lots of things being used. So there was a shortage of copper. So General Groves and Colonel Nichols knew that they were going to need something to build all these coals. So Colonel Nichols said, let's borrow some silver from the Treasury Department. Silver is as good an electrical conductor, not better than copper. So Colonel Nichols goes to Undersecretary Bell, the Undersecretary of the Treasury, and says, Secretary, we need to borrow some silver because there's a shortage of copper. We need to use it as electrical conductor. Now, Undersecretary Bell says, sure, we've got some reserve. How much are you going to need? Colonel Nichols is thinking, and he said, I'm going to need several thousand tons. Secretary Bell says, Colonel, you don't understand. Here at the Treasury, we don't think of in terms of silver, in terms of tons. We think of it in terms of troy ounces. So Colonel Nichols figured on the back of his envelope and said, well, I need about 300 million troy ounces. What he got was 14,700 tons of silver and used it to wind these coils. Each one of those ridges you see around it there is a magnetic coil. The Calutrons, remember this vacuum chamber goes between those coils. Now, they borrowed 14,700 tons and used it to wind those coils. Now, they didn't return that silver back to the Treasury. They kept asking for it back, but they didn't return. They returned a lot of it in 47, 48, 1947, 48 time. But they kept 67 tons of that silver. If you could find me that, just keep going till we hit that 9731 bill. Next one, next one, right there. That's the first building completed on the site, building 9731. And it had 2 alpha K-Trons. See, there's coal here, coal there, and coal there. So you got 3 magnetic coals. And in the middle is where the K-Tron is. It goes in at the bottom, makes that hash circle, and comes out at the top. These are the betas. There were 3 beta coals and 2 beta K-Trons. They're located in either end of that building. Now, these were wound in silver. So when they shut the K-Trons down in 1946, because they could now get the uranium-235 from the K-25 gaseous diffusion process, a continuous operation that could operate at a 10 cost of Y-12. They shut them down at Y-12. But they kept these 2 sets operating in building 9731. They operated until 1970. In 1970, they took these coals out and took the silver out of them, cut it up in little pieces, shipped it back to the treasury. Now, one of the things that Y-12 brags about is the fact that they borrowed 14,700 tons of silver from the Treasury Department, took it out of the Westmore Depository in New York, brought it down here, and then turned it back. And in the calculations, they only lost less than 1/10 of 1% of what they borrowed. Now, Lee, if I have a savant in the room, they'll tell me right quick that 1/10 of 1% of 14,700 tons is a pretty good chunk of silver that we lost.
And then what would be the value of that at that time, roughly?
They estimated that was at about $400 million.
That lost or the total value?
Oh, the total value.
Okay.
Total value. So that's a silver story.
Now, did they had to process the 14,000 tons, put it into the shape of wires? They had to.
And the wire was about 4 inches wide and about an inch thick. And they wound those coils.
So they had to melt the silver and cast it in wires.
They did.
Did they return it in that form? I wonder.
Actually, they pulled it off of the coils and chopped it in 3-foot lengths. And then they stacked it up on pallets and put it on trucks. As pallets of 3-foot lengths, that's silver.
Probably the way it is now still.
I would expect, and they've told me that up at the treasury, that they still have that reserve, just like it came back from Venezuela. I hope that's it. Any questions about the silver story yet?
I have a question about mercury.
Okay. Now, unlike the silver, we lost a lot of mercury.
Yeah,
a lot
I
of
know.
it.
I was
Not like the silver.
I worked in one of those alpha buildings for
Yes.
fusion factory. And there was a lot of mercury under that building.
Yes, Alpha 2 is the one you were in.
That's
probably.
right. That's
Yes.
correct.
There's a wet weather spring under there that brings
So,
that out.
so why did they need the mercury?
Now, the mercury was used for later. It was used from 1953 to 1955 to 1963 to separate lithium-6
Okay,
for the hydrogen bomb.
I see.
Okay, and now the reason it's in Alpha 2 is because there was a laboratory process down there that proved the principle. Then they went up to Alpha 4 and Alpha 5 and built the Colex process, column exchange. And that's where the huge amount of mercury. We had all of the nation's reserve of mercury down in Oak Ridge. And that's where the spills took place that actually got into the East Fork of Poplar Creek. And one of the major issues in Oak Ridge right now is cleaning up that mercury. Okay?
So, yeah, there was that all hit the press.
In 1983.
Yes. Where the missing mercury. And Yeah, because you can, was that what it was? The missing mercury, I guess. Was that this?
Now, there was a mercury report that was done, that was released in 1983. And there was a huge public relations nightmare in dealing with that.
Because it was unaccounted for.
Not accounted for.
Because you knew how much you needed in this chemical purification.
Right.
You had a good estimate how much was lost in the streams, but there was a missing amount.
And the reason is they did not in all cases account for all of the mercury they were getting. So they would get now mercury comes in a flask, about 2.5 gallons, and about 8 to 10 inches just a container. And they were shipping those in and bringing in all of the things bring in, and then they were dumping them in that process. Large amount.
Yeah,
And
why?
I'm not sure it was all accounted for.
Well, I don't think it was, but I was working for Senator Baker at that time. I spent the year in DC. And that hit the paper, so he sent me down to find out the story. Where's this mixing mercury? I don't remember the details, but my memory of it is it was a round-off error.
Yeah.
That when you have two huge quantities, that you're measuring all of this, mercury coming in and mercury coming out, the volumes, the quantities are so large that it was a round-off error, that there's some uncertainty of measuring masses that big in volumes, both in and out. And my conclusion then, as I recall, it was just a round-off error.
Yeah, that's true. They did know that there was a significant amount of it that got into the stream.
Yes.
And went offside. And they did know that they still had a significant amount there. But there was a difference in the calculation.
Yeah.
Bill Wilcox actually led the team that did that mercury study that produced the report that showed that.
I probably met with him at that time in
Yeah, you did.
83 or 84. Yeah, so that's, there's a lot of, by the way, there's a lot of sins of the past in Oak Ridge, but we didn't understand. Marie Curie died at age 67 due to sort of leukemia, due to all the radiation that she had worked with in discovering elements, polonium and radium. Yeah.
Did she know that was why she was dying? How much she died? Or did they find that out later?
I think she knew, because I think it was she that, when she would get a flask of separated radium, she would stick it in her pocket and carry it around for some days. And then apparently she developed burns on her skin where that was in her pocket. So she knew after the fact that this was not good on the body. So she probably knew that. I'm not sure. And by the way, apparently still her log books, her laboratory records, her log books are still radioactive. They're sealed up. You can't read them without special gear because her books are radioactive. So yeah, it's not surprising she died. That's amazing to me. She lasted to age 67. Still, and so by Manhattan Project, even after Manhattan Project, we knew that radiation wasn't great on living things. And it was being used already. She started the Radium Institute to treat cancer with radium. But we had no idea of the low-level impacts of radiation. And so people took care at Oak Ridge in the 40s and 50s. But when you finish your experiment, you would bury the, your test tubes and gloves and such in the ground, in canisters, for example, but still bury them. Well, they all leak. And 50 years later, there's a massive cleanup at Oak Ridge and Hanford and various cases where we did not understand in the 50s how important it was to really isolate radioactive, low-level radioactive material. So there's still a lot of cleanup going on at Oak Ridge, right, Clay?
That's correct.
Huge amount of money. Anything else?